In the first set, we covered basic material and are now ready for more advanced topics, such as the state space for qubits and that for qubit pairs, general mixed states, and entanglement beyond the 2-qubit situation. In this lecture, we remind ourselves of the key elements discussed in the first set of lectures. We begin the second cycle with a review of some of the things we learned in the first cycle. So, as a reminder, we describe quantum systems, ideal quantum systems, by kets, say like ket 1 and ket 2 and ket 3 and so forth, or also could be labeled differently, say by A and B, whatever are the circumstances that suggest the labels that we use. And these kets can be combined into new kets by linear combination. So for example, I can take ket 1 and multiply it with the complex number alpha. I add to it ket 2 multiplied by the complex number beta, and that gives me ket 3. So there could be relations like this. And so if we picture this relation as ket 1 and ket 2 points in some space, then these linear combinations, they kind of tell us that all kets that refer to points along such a line are also in the ket space. Now, partners of the kets are the so-called bras, for which we have this notation. So there will be bra 1, and there's bra 2, and then there's bra 3, and so forth. The bra that goes with the label A, bra that goes with the label B, and more of them. And also those bras can be combined into new bras by linear combinations. In particular, if we start with the ket 3, then the relation that turns the ket 3 into the corresponding bra is what we call taking the adjoint. So we have this adjoint symbol. Then that will give us the bra with the label 3. And so since 3 is this linear combination of 1 and 2 in our example, we will have the ket 1 times alpha plus the ket 2 times beta and the adjoint of that. And that is simply what we get by taking adjoints of the individual terms and then adding them up. So the adjoint of the first one is the complex conjugate value of alpha times the adjoint of the ket 1, which is the bra 1. And then we have the complex conjugate value of beta and the bra, that is the adjoint of ket 2. So that will be bra 2. So we have a linear space for the kets. And we also have a linear space for the bras. And these two linear spaces are related to each other by the adjoint. So for every ket in the ket space, there is a corresponding bra in the bra space. And for every bra in the bra space, there's a corresponding ket in the ket space. So like having the bra 3, I go back to the ket 3 by taking the adjoint. And so that just says, if I begin with the ket 3, I take the adjoint, and I take the adjoint again, then that amounts to doing nothing. And similar for the bra. If I begin with the bra 3, I take the adjoint that turns it into the ket 3, I take another adjoint that takes it back to the bra 3. So we have this one-to-one relation between kets in the ket space, bras in the bra space, and that operation that converts one into the other is what we call the adjoint. And we remember that it involves complex conjugation, in particular for such coefficients that appear in linear combinations. So we have the linear space of the kets and the linear space of the bras, and they are related to each other by this operation that we call take the adjoint. And then let me further remind you that if I have a bra, say bra A, and a ket, say ket 3, and we can multiply them and form the so-called bracket, which is, as you remember, the bracket product with all the properties that we associate with a product. So in particular, if 3 is this linear combination of 1 and 2, then we have for this bracket of bra A and ket3, we can also evaluate this as the bracket of A with ket1 multiplied by the number alpha plus the bracket of A and 2 multiplied with the number beta, and so forth. If we have a linear combination of bras like this, then we have the corresponding statement. And as another property, we remember that if I interchange the roles of the bra and the ket, then I get the complex conjugate number. And if I take from the bracket of the bra, which is the adjoint of the ket that appears here, so then this is a number which is always positive, and we get the equal sign only for the null bra or the null ket. So all these properties together say that the bracket formed of A and 3 is an inner product of the ket A with the ket3, and it's also an inner product of the bra A and the bra 3. So these are inner products. And then if I have an inner product, I have the concept of length. So the length of the ket A, so the length of ket3, well, that would just be the bracket of 3 with 3, and then I take the square root of that positive number. So it's the inner product of 3 with itself, and then the square root of this number. Or if I read it as an inner product of bras, I get the length of the bra 3. So the length of the ket3 is equal to the length of the bra 3, which I get from taking the adjoint of the ket3. So now these linear spaces are endowed with inner products. So this is a linear space with an inner product. And this is a linear space with an inner product related to each other by taking the adjoint. But such linear spaces with an inner product, and with the additional property that if I take these linear combinations with complex coefficients, then all such linear combinations are new kets or are new bras with no exceptions. That tells me that these inner product spaces are so-called Hilbert spaces. So we have a Hilbert space of kets and a Hilbert space of bras. They are related to each other by taking the adjoint. And they are closely related to each other by the inner products themselves, because the inner product in the ket space actually involves a product with the, a bra from the bra space, and the inner product in the bra space involves the product with the ket from the ket space. So we have the linear space for the kets, the linear space for the bras endowed with the inner product. These are Hilbert spaces. And now we can also multiply the ket3 with the bra A, but in this order, and that product is then a ket bra, and these ket bras are operators. So a general operator is a linear combination of ket bras. Say an operator A, and this operator applied to some ket gives a new ket, and the operator applied to some bra gives a new bra, and And that is illustrated by taking this kit bra and applying it to an arbitrary kit. Well, that gives us the kit 3 and the bracket of A with the generic kit. And likewise, if we apply it to the bra. So an operator applied to a kit is a new kit, an operator applied to a bra is a new bra, which means that the operators maps kits on kits and they map bras on bras. Now, in this Hilbert space, we also have a basis made of a set of kits AN, and this basis is usually chosen to be orthonormal, meaning normalized and orthogonal. So if I take the kth and the lth ket in the basis, then the inner product is 1 if it's the same basis element twice, and it's 0 if it's 2 different basis elements. So 2 of those basis kets are orthogonal, inner product is 0, and they are of unit length. Each of them is of unit length. And it's a basis in the sense that if I have a generic ket, I can write it as a linear combination of those basis elements. So I'm summing from k equals 1 capital N, the number of basis elements in an n-dimensional Hilbert space. So here I have the kth basis element and the coefficient alpha k. So it's a linear combination of this kind, but formed with these basis elements. And these alpha k basis coefficients, while they themselves are obtained as the brackets of the kth ket in the basis with the generic ket that I want to expand in the basis. And so this alpha k is just equal to ak and a, so the inner product of the basis element with the ket in question. And so if I factor this, again reminding you of what we have seen before, I get the sum of all the ket bras from the basis element applied to the generic ket, and that whole thing is equal to the generic ket. So this sum is just equal to the identity operator, the one that maps every ket on itself and every bra on itself, for which we write 1. And so this statement is a completeness relation. So these bases are complete, meaning that every ket can be expanded in these basis elements. That's the notion of a basis. Now, there's not just one basis in the Hilbert space. We can have another basis. And let me denote this by B1, B2, all the way to Bn. And again, it will be orthonormal and complete. Just like the A basis is orthonormal and complete, so also the B basis is orthonormal and complete. So now if we have the two bases, we remember that we can form a unitary operator by combining the kets from one basis with the bras of the second basis, because of course if I have a basis of kits, by taking the adjoint I get a basis of bras, and I can do that for the A basis, I can do this for the B basis. So here we have the kits from the A basis and the bras from the B basis, and the adjoint operation, the adjoint unitary operator, just has the roles of the two bases interchanged. So I will have the BK kets and the AK bras, and clearly these unitary operators map the kets and bras from one basis on the other. So for example, if I apply the U operator to the kth ket in the B ket basis, I get the kth ket in the A basis. And likewise by applying them to brass, and similarly for doing the same thing with you adjoint. And I already said that these operators are unitary, which is just saying that applying u and u adjoint in one order or the other gives the identity. So we stopped here with this review because there's a few more things that we need to also recall from the first cycle, but we will do that at the beginning of the next lecture.